Hello everyone, good evening. This is the NPTEL problem solving session for the course Introduction to Algorithms and Analysis. This is week 12, and as usual, I will discuss some of the problems related to this week's assignment. And while discussing the problems, I will also discuss a bit of theory to help better understand how we approach the solution. Uh, right, so the primary topics that were covered this week were discussion, in-depth discussion on dynamic programming. And within dynamic programming, there was uh, explanation of memorization and subproblem, right? How do we identify the subproblem, right? And like the examples of dynamic programming were given using the Fibonacci sequence prediction, Fibonacci sequence prediction or Fibonacci number prediction, and the shortest path algorithm. So a dynamic programming based approach was discussed for both of these problems. Then there was a discussion on guessing and the views of directed acyclic graphs. And finally, there was a note on computational complexity. So what we are going to do is we are going to take some problems that are related to the earlier parts of this week's lecture, and we'll take we'll go through some of these sections, the theory of some of these sections, when we are about to take a problem for that particular section. So let's start with uh, the problems. So the first one is which one of the following statements is true? So statement one is the value of any flow is bounded below by the capacity of any cut statement 2 in a flow network the maximum amount of flow passing from the source to the sink is equal to the total weight of the edges in the minimum cut, right? So which of these statements is true, right? So again, if we look at last week's uh, lectures, right? So there was discussion on graphs and graph cuts and the bounds on the flow values for cuts for the capacity of a particular cut, and we had a theorem, right? So for an upper bound on the maximum flow value, and the theorem was the value of any flow is bounded above by the capacity of any cut, right? And like for the proof of it, we had the value of a flow as uh, described by f of s and t, where s and t are the two different sets in which we have made a cut, right? With the value of flow for this particular cut, right? And this is calculated for all the vertices belonging to S and belonging to T and adding up the individual flows between the pairs of vertices. And this value is less than or equal to, of course, the value of the cut between U and V, right? Between any two uh, vertices, between S and T, like two graphs, we can say, or two subgraphs made by the cut, right? So, of course, we can see that this is the capacity of that particular cut, right? And clearly, the value of the flow has an upper bound that is given by the capacity of the cut, right? The value of the flow cannot be more than that. So clearly, uh, statement one is false, right? Because it is not bounded below, it is bounded above by the capacity of any cut, right? The value of any flow is bounded above, not below, right? So statement one is false. Now let us try to look at statement two. So in a flow network, the maximum amount of flow passing from source to the sink is equal to the total weight of the edges in the minimum cut, right? So this is, of course, statement two is true because when we have the minimum cut condition, right? So for a minimum cut, the flow passing from the source to the sink will be the maximum. And the maximum amount of flow from the source to the sink is equal to the total weight of the edges in the case of a minimum cut. Right? So statement 2 is again true. Right? So and this can also be seen by the theorem that was discussed at the end of the uh, last week's lectures, was by max flow min cut theorem. Right? And the theorem is, right, that the following statements are equivalent, right? And what are the following statements? Right? That F is a maximum flow, or F admits no augmenting paths. So it means F is the minimum cut. Or we can also say it like this, that F is equal to the cut, uh, like the value of the flow is equal to the value, like, cut for some cut. So uh, for SNT, so it has reached the upper limit on the flow, right? So this upper limit can be achieved when there is a minimum cut, right? And this condition is called that F has a maximum flow, right? And for that, of course, there have to be no augmenting paths. So all of these statements are equivalent, and this is essentially the statement 2, right? That in a flow network, the maximum amount of flow from the source to the sink is equal to the total weight of the edges in the minimum cut, right? And the total weight of the edges in the minimum cut will be the entire flow, right? When there are no augmenting paths. So again, uh, statement 1 false because it is bounded above, not below, and statement 2 true, right? Because it is the statement directly. Let's take another example. If F be a flow on the graph G, the residual network given by GF for the same vertices, but the edges of the F is the graph with strictly positive residual capacities if a if the CF between U and V is equal to the C of U comma V minus the actual flow between U comma V, right? And this is greater than 0. Or the capacity of the residual network is equal to the flow minus the original, and this has to be positive, or c comma v, c of u comma v minus f of u comma v, and this is negative, or d f of u comma v is of u comma v minus c of u comma v, and this is negative, right? So we have to basically uh, use the residual network, uh, like we have to analyze this residual network, right? And these are basically the theorems, or the definition of residual networks that we have encountered in lectures, right? So let us just discuss what a residual network is, right? And the definition of a residual network is, let f be a flow on the graph G. The residual network GF v comma EF is the graph with strictly positive residual capacities, right? And what is the residual capacity, right? So residual capacity is the capacity on the residual network, right, between any two vertices u and v, right? And that is uh, the capacity on the original minus the flow u comma v. And we know, like from the above results also, that this value has to be positive, right? So this has to be strictly positive, right? So what does this mean? This mean that edges in the residual network admit more flow, and we can take even an example for it, right? So if the network G is like this, we have two nodes U and V, and we have capacities given like this, right? So the residual network can have, or will have, these capacities, right? So of course these edges, right, they admit more flow than as compared to the original one, right? And there was also a lemma related to this, that the number of, or the uh, right, so this is less than or equal to 2 times the original uh, value of the edges, right? So yeah, for this, comparing all the options, option A is the correct answer, right? Because even for option D, this inequality still like holds, but the residual capacity cannot be negative, right? It has to be strictly positive. That's why only option A is correct. So let's take another example. Dynamic programming can be solved by which of the following steps? So A, guessing and memorization. B, recursion and guessing. C, guessing, memorization, and recursion. Or D, none of these. Right. So this week there was an extensive discussion on dynamic programming, right, and how to identify problems where dynamic programming is applicable. And we saw that uh, we use dynamic programming, or dynamic programming is very useful in problems where recursion is involved, and we can memorize and reuse some uh, previously calculated results of sub problems, right? And therefore, it is um, right. And while identifying recursion and using memorization to perform recursion, we also use guessing, right? We guess basically to design a recurrence, right? Um, and to find the best guess, we actually try all the choices of, let's say, in the graph that we have formulated, right? In the graph that we have constructed for our original problem, right? And for all the choice of vertices, we try the guessing to get the best uh, arrangement of the problem in the format if it's a problem and use the best one, right? And uh, so so from lectures we know that it uses all three, right? It uses guessing to get the best uh, possible way of recursing over the subproblems. We memorize the subproblems that we have solved once, and then we use recursion. And while doing recursion, we use the memorized solutions to reduce our computational time drastically. Right. So if we were just to, right, uh, go how we actually go over a problem. So, right, how do we guess? Because recursion and memorization, I think we already know, right? But guessing is used for basically how to design recurrence, right? And for the graph analogy, we want the shortest path from source S to goal V, right? So it starts from S and it goes through some vertices to V, right? And we want this path to be the shortest, right? And what is the last edge, right? We do not know the last edge, right? Because we don't know beforehand what path we'll end up taking to reach V finally, right? If there are multiple uh, incoming edges to V, then we don't know which edge leads or which edge belongs to the shortest path, right? So guess the what we do is we guess the last edge as just some, right? So just some edge that is going to V, right? And so the path is shortest, right? So S to W path plus the edge U comma V, right? Because again, this is when we assume that there is an optimal substructure, right? So then um, we right, we can perform recursion, right? Because for this, the cost is whatever the cost is to go from S to W plus the weight of the edge that we have assumed belongs to the shortest path, right? And this is basically another subproblem that can be solved in a similar way, right? And to find the best guess, we have to basically try all choices, right? And in finding the solution for this, and when we are trying all the choices, that is where DP helps us, right? So of course, DP uses all three, right? Guessing, recursion, because we saw that there is a subproblem uh, structure, right? Optimal substructure uh, that can be formed here. And because many substructures will be repeated when we are searching for the over the entire space, right? We need to speed it up using memorization, right? So that the time complexity is not exponential, right? So DP uses all three, right? Guessing, memorization, and recursion. Let's Take another example. Halting problem is an example of what kind of problem, right? It is decidable problem. It is undecidable problem. It is a complete problem. Or is it a trackable problem, right? What kind of problem is halting problem, right? So let's try to look at what exactly the halting problem is, right? How is it actually defined, right? And so it is defined as given a computer program, does it ever halt, right, or stops, uh, right? So basically, if we just have the computer program and no specification of it beforehand, and we just run the computer program, can we prove that this computer program ever comes to a stop, right? So of course, this is an uncomputable um, problem, right? Because there is no algorithm that can tell us beforehand for any computer program when it will come to a stop, right? We have to, without running the program, of course. Right? So it's not a real number. So no algorithm currently exists that solves it, right? Uh, or solve it correctly for in finite time, right? For all inputs. Right? And of course, it's a decision problem, and most decision problems, right, for which the answer is a binary, right? A program comes to a halt or it does not, right? It's a binary answer, a yes or no. So most decision problems are uncomputable. Uh, Uncomputable, right? It can be like there can be many examples that a program has, right, binary strings, right? And it can be, right, that we are searching for non-negative integer, right? A non-negative natural number. So, of course, if we are searching for a non-negative integer, we can't uh, tell beforehand if the program will come to a halt or not, because it might try to search forever, right? Because there is an infinite sequence of bits, right? And for again, it has to be for all inputs, right? And it's again, it's a decision problem, right? So the program where you're given a binary string and you have to say that if it is a non-negative integer or not, right? So again, it's a decision problem, right? Where the function that we are making, right, takes a binary string as the input, right, and it outputs a yes or a no, right? And we basically check for non-negative integers, right? And the issue here is that, you know, the function can have, or the input can have, infinite sequence of bits, right? Because it can be, the input can be any real number, right? It can be any real number. And even if, right, the number of non-negative integers is a subset of all the real numbers, and of course it is very, very less than the number of real numbers, it's still uncountable because R is uncountable, right? Because again, there are infinite number of non-negative integers, right? So, of course, for this particular example, the halting problem is an example of undecidable problem, right? We cannot solve it. It cannot be solved by any algorithm, right? That's why it is undesirable, undecidable. Let's take another example. Which kind, or which of the following problems is not solved using dynamic programming? So is it the binary knapsack problem, or the matrix chain multiplication problem, or the edit distance problem or the fractional knapsack problem. Right, so which one of these algorithms is not solved using dynamic programming? Right, and like of course we know from the lectures that the above three are indeed solved using dynamic programming, right? But the fourth one, right, it's actually solved using greedy algorithm. And the fractional knapsack problem, it's solved using the greedy algorithm, right, and not dynamic programming. So, of course, the solution for this example is C, no, D, fractional knapsack. Let's take one more example. In computational complexity, which of the following subsets inclusion is true, right? So the notation here is similar to the one that is explained in the lectures, right? So P is basically the polynomial time. E is or the problems that take polynomial time. EXP is the set of problems that take exponential time, right? Problem solvable in exponential time, and R is basically the set of problems solvable in finite time, but using recursion, right? That's what R stands for. So which one of these subset inclusion is true, right? R, P, D, none of these, right? So if we take a look at the definitions of these, right, this will become much apparent and clearer, right? So P is a set of problems solvable in n to the power c time, where c is some constant that is very, very less than n, right? It means it is polynomial time, right? Exponential exp is the set of problems solvable in 2 to the power n to power something, right? So exponential, right? So in exponential time. And R is the set of problems that are still solvable, right? It's not like it's a halting problem that we know it just we don't know how to solve it, right? These are problems that are still solvable, but infinite time, right? And prime example is recursion, because we saw that the computational complexity of recursion is basically even greater than exponential, without using dynamic programming or other tricks that we use to speed up recursion, right? And if we plot it on a scale of computational difficulty, right, where some point we say that the problem is uncomputable, right, or it is undecidable because it takes so long that we just cannot run it for long enough, right? So this is the polynomial time, right? Very much tractable, very much computable. This is exponential time. So again, it is still tractable, but it takes a lot of extra time compared to the polynomial time. And when we are just talking about finite time, right, it is just uh, before the limit, just before we hit the limit of uncomputability, right? That we have uh, problems that are solvable in infinite time, but we don't know how, like, it will take much longer, even when we compare it to the exponential, right? So the relations between these problems, right, is this. There is no equality, and all the problems that are solvable uh, come under, let's say they come under set R, right? They that are solvable in finite time, right? So the problems that are solvable in exponential time is a subset of R, right? But again, these two cannot be equal, because for exponential time we know that we know the upper bound of time, right? It is exponential. We still have an expectation of how much time it will take. And similarly, uh, like the cost for the polynomial time is again a subset of the problems that are solvable in exponential time, right? Because again, we can change, for example, the Fibonacci sequence problem, right? It takes as exponential time originally with the naive recursion algorithm, but using dynamic programming, we can then convert this problem into having polynomial time. But again, these sets again cannot be equal, uh, because polynomial time is much lesser than exponential time, right? So this is the correct inclusion, right? That R is the biggest set, followed by exponential, followed by polynomial, and they cannot have equality in them, right? So out of all the options that we have, option C matches our understanding, right, of the set of all the problems that are solvable in finite time and its subsets for exponential time and polynomial time. So I think this will be helpful for solving this week's assignment problems, right? And I will stop the meeting now. Thank you.